Hello everyone, my name is Charlie Arginello and I will be presenting my project on using machine learning models for network intrusion detection systems. A little bit of an introduction. Exploring how machine learning can enhance network intrusion detection systems, which are essentially like security cameras at a house or a building. They are a system put in place to monitor and alert if something happens. And by doing this, we want to curate the CIC IDS 2017 dataset to reduce false positive and negatives in realistic network traffic. Cyber attacks are growing in frequency and sophistication, so making traditional rule-based NIDS systems are useless. By applying machine learning models, introduces adaptability to threat detection, which is crucial for enterprises, government agencies, and service providers. And by developing machine learning models that read from this data set and comparing them to current research, we will show how machine learning models are a great way at detecting benign and attack traffic correctly. So, traditional network intrusion detection systems are incapable of detecting modern evolving network attacks due to outdated datasets. Large datasets like the CIC-IDS 2017 require extensive cleaning, which we will show later on. And the need for machine learning models that can accurately detect false positive and false negative threats is very important because with the traditional network intrusion detection systems, they use rules put in place or they only detect anomalies and then generate reports and alerts. So it still needs the IT person or anyone in computers that are doing threat analysis to create these rules so that it'll detect it, where machine learning will learn and become better as it learns on this traffic. So some of the problem objectives are we want to pre-process the data of this data set. So by doing that, it makes it so that when we run these machine learning models on this data set, it gives us the most accurate form of these models. We want to clean the data that is relevant, such as infinite NAN values and non-numeric data. We want to train the MLP, SVM, and ID3 models. We want to measure their performance with 4 benchmarks: the confusion matrix, precision, recall, and F1 score. And we want to achieve 95% detection accuracy. In figure 2, we can see this is basically how creating a machine learning model looks like from a raw traffic data set and how we are able to create a training and testing data set and then be able to create alerts. So for the literature review, most of these studies used different machine learning models on the CIC-IDS 2017 dataset as well as many others. A lot of them had different key findings. They all had very high accuracy of their models, but the way they were able to create these high accuracies was interesting. So for the first article, high accuracy with proper pre-processing of data created the highest accuracy. So as explaining before, like when we pre-process the data, we want to ensure that the data is processed correctly so that we can obtain a very high accuracy. The gap in this article was that it eliminated the use of IP and destination ports due to high cost. This is something we addressed. We did not get rid of these data points within the data set and still maintained high accuracy. The going on like data splitting, so 90% training, 10% testing gives best results. This doesn't really work though because it doesn't mention what data needs to be cleaned to obtain the best results. And by giving it a 90% training and 10% testing, it's almost like giving them the answers to the test. So it's not really a very accurate way to do this. Um, in the third article, they use a multitude of machine learning models, but they notice that the importance of weight groups are necessary. So for MLP, we will see that certain weighting is necessary. They used a single layer MLP, which is something we addressed with using 4 layers. And then for the last one, they use MLP with SA to have the highest accuracy on all data sets they tested. But because of this, class imbalance caused low accuracy. So ensuring that the classes used for testing these models are balanced properly will give you better accuracy. For the comparison table, we can see our study against 2 others. The NA values in the table were models they didn't test in these articles. So we can see our study for MLP, it was very accurate, 99% F1, 99% precision, 98% recall. SVM dropped down to 82%, 84%, and 80, and then ID3 was 96%, 94%, and 98%. And we can see that our MLP was way more accurate than the second article's MLP, and we can see that the ID3 was more accurate than their ID3. And then for the third article, they did not use F1 score as a benchmark. So by seeing this, they used precision and recall, and they had very high accuracy, which we found ours didn't. And this is because for all 3 models, we use the same pre-processed data. So by doing that, this data wasn't processed properly for the SVM model, so that's why we saw a little dip in accuracy. So for the scope and limitations, basically the scope of this whole project is we want to create machine learning models using the CIC-IDS dataset, but with this comes limitations. So the time to make these models takes a very long time. You have to clean the data, pre-process the data, then you have to actually create the model within the code, and then you gotta create the evaluation and make sure this is all working. So this took a very long time to do. We had no encrypted traffic analysis, so everything was labeled. So by using encrypted traffic analysis, which is realistic in today's world, this would make it way more accurate. There was no use of deep learning models, and the use of a single data set really narrowed down the scope of this project. So by using multiple data sets, we would be able to get multiple benchmarks for how accurate these models actually are. So a little bit of methodology. This is the graph I created for this. So you can see at the top we have the data input, which is the CIC-IDS dataset. Then from there we pre-process the data. So by cleaning, encoding as binary, benign 0, attack 1, normalizing the data using the standard scalar library, and feature selection, so dropping values we don't want, such as non-numeric data and NAN values. Then from there, we actually implemented the machine learning models, so the multi-layer perceptron, the support vector machine, and the ID3 decision trees. And then once those were created, it then went to the evaluation model, so confusion matrix, so true negative, true positive, false negative, false positive, the total overall accuracy of the model, the precision, the recall, and the F1 score, and then it then created a prediction output. So is this benign or is this attack? This is specifically for the ID3. So a little bit about the tools used. So Pandas is a library that allows for the use of imported data sets. So by using the CIC-IDS dataset, we were able to import it into this code. Then Python was used for its extensive libraries and ease of use. NumPy is a library that contains high-level mathematical functions such as the weighting It uses very high-level mathematical functions such as linear algebra and many others to do these. So by using this library, it allowed us to create these models. sklearn provides the actual machine learning algorithms that split and train the models and then evaluate them. Matplotlib was used to turn raw numbers from pandas and numpy into visual charts for the ID3 specifically. Glob is a library used to gather all files within a folder on your computer, and then OS is used for file path management, so actually reaching that specific file path to your computer within to get those files from that folder. You had to use that library, so OS and Glob go hand in hand. And then Gemini was used to help create / debug the prototype models and fix any errors that occurred. So it helped that debugging a lot. And we can see in this figure, it lists all those libraries and their functions that specifically come from. So this is for the ID3 tree, so we can see the plot tree function, the train test split function, the accuracy score, classification report, and confusion matrix. These are all functions within these libraries. For the data cleaning, this is a snippet of the code. So first, we define the data set as a function clean data set. And then with this, we're able to show the original shape and the clean shape. So what it looked like before cleaning and what it looks like after cleaning, then replacing any infinite values or NaN values and converting numeric like columns such as flow bytes in flow packets to actual numeric types, and then print out the NaN values before dropping to show like how much it actually did drop. Here is the actual code output showing the data being cleaned, so we can see that the original shape was 2,830,743, and then we can see after it was cleaned it was 2,827,876. So it cleaned it, all the things we didn't need, and then you can see a little bit underneath the pre-processing data for binary MLP. We can see it splits the two into training and testing, so this allows the model to be very accurate. So for pre-processing the data, this is the code showing how the training and testing data are split. So first we print out like the section like, hey, this is the pre-processing part. Then we convert the labels to binary, so 0 and 1. And then from there we separate features into X and Y targets. Then we split the actual data using the train test split function we saw earlier that is part of the sklearn library. And then we use standard scalar function to actually scale these features, and then we output the training samples and testing samples. So this is the actual MLP model. So we can see that the hidden layer size is the first hidden layer of this. So this layer has 100 neurons as specified by the first number in the hidden layer size, so 150. The input layer is the layer this layer receives the features of your actual data set. The second hidden layer is 50 neurons, but is specified by the second number in the hidden layer, so 50. And then the output layer, this is the layer produces the final prediction of the model. And the number of neurons in this layer depends on the task. So 1 neuron for binary classification, multiple neurons for multi-class classification. So something we used was Atom. This was an algorithm that acts as a coach to basically update the weights while running to increase the accuracy of the model. And another thing we added was no iteration change. So if the model doesn't see improvement after 10 iterations, it'll automatically stop the model. And we made the max iterations 300 so that it has a pretty good chunk of data for the results. And then to ignore warnings, we used the with warnings function. So this made sure that like anything that would cause a warning would stop. So for the SVM model, it's pretty similar to the MLP. We have the max iteration of 300. We have the early stop if there's no change. Another thing that was added was the validation score. So this essentially acts as a test. So it grades the accuracy of the model. And if it sees that this grade is not increasing, it's either not changing or decreasing, then it'll stop the model. And then it prints out the results. The ID3 model is a little simpler. It uses the decision tree classifier function of the sklearn library. And a little bit later on, we'll see like how it actually looks in output. So for the MLP evaluation, it uses the predict function. It uses the accuracy score, confusion matrix, and classification report to basically give a good screenshot of how accurate this actual model is. For SVM evaluation, it's the same thing. We use the predict, accuracy score, confusion matrix, and classification report to show how accurate this model was at detecting benign and attack traffic correctly. The ID3 is the same as before as the other two, but for this we use the visualization of the tree to show how the ID3 tree actually worked. So basically, like there's a certain amount of rules you set in place so that it makes decisions. So we basically made these rules here. So we gave them class names, feature names, and just basically building what the plot will look like. Some challenges we ran into were opening all files from a data set. So this took research to understand like how am I able to open all these files from my folder in my computer. So this took some research at finding out what OS and glob actually do. For iteration count, originally we had a very large iteration count, but it was causing the model to be very slow and never ending. So it was very hard for testing to actually get results that we could evaluate. So by setting an actual cap that if there's no change in performance after 10 iterations, this allowed for us to get data that we could evaluate and compare to previous research. Installing the libraries needed, it took a lot of research at basically needing to find out which libraries were needed, and then cleaning the data. You have to know which types of data in the data set you don't need, such as infinite and NAN values. And this figure is basically showing the challenges faced when accessing all files. So this is what the actual code looks like. So it uses a folder path to open it. So OS is used to join the path, and it looks for all CSV files, which is what they were. And then glob basically combines them all together into one file so that it's able to be read. So from the results for the MLP, we can see it had very high accuracy of 99.53%. The confusion matrix basically shows the data tested and the traffic that was labeled correctly. So we can see 679,966 benign traffic correctly labeled as normal, so true negatives. The true positives of 164,416 was attack traffic correctly detected. 1,430 was false positive, so this is benign traffic wrongly flagged as attack. And then false negatives was 2,551, so attack traffic mislabeled as benign. And we can see that the precision, recall, and F1 score for benign traffic was perfect at 100% accuracy, and we can see that the attack for those three was just short of 100% at 99, 98, and 99%. This was the most accurate model that we tested, and we can see on the left this figure basically shows the actual output of what it looks like once the model is being done, when it's done running. So for the SVM, we can see that the overall accuracy was not that high at 93.07%. This was below our benchmark. The true negative at 655,904, so this is good. It labeled this as normal traffic. We can see the false positives went up, so we can see it's 25,492, so this is benign traffic misclassified as attacks. We can see the false negatives, which is a very dangerous benchmark. So we can see 33,328 were attacks misclassified as benign. And then the true positive was 133,639. This is attack traffic correctly detected. And we can see that the precision recall and F1 score, so for benign traffic, it was still pretty good. It was above that 95% benchmark. But when we see the attack for precision recall and F1 score, it dips way below that at about 84, 80, and 82%. And this is due to the data not being pre-processed properly for this actual model to run to the highest accuracy. So the results for the ID3 were really good. They were 98.44% above that benchmark. We can see the amount of true negatives was 671,615. The false positives was 9,781. False negatives 3,483. And true positives was 163,529. And we can see that the precision recall and F1 score of benign traffic was just a percent low of 100 at 99% for all of them. And we can see that the precision recall and F1 score for attack traffic was 94, 98, and 96. And then on the left is another screenshot of the actual code output showing what this code or what this model actually creates and the accuracy it shows. So moving on, this is the plot we showed earlier in the code. This is the actual ID3 tree rules. So first it asks a condition to see if the standard deviation is less than or equal to 1.382. It then makes a decision if that's true or false. Then entropy measures the impurity of the data, so how accurate is the data. Sample is the number of rows of data. Value represents benign and attack samples, and then class represents the majority vote. So you can see that orange is classified as benign and blue is classified as attack, and you can see there's some light orange and some light blue. This is because it is on the edge of being either benign or attack, but there's just enough data to make it one or the other. This is my timeline, so I used a Gantt chart to basically break down how I was able to create and research all these machine learning models. So the proposal draft took about 2 weeks, the midterm presentation, and then the final presentation took the longest because of creating these actual prototypes of machine learning models. This took about 21 days to do. So this took a big chunk of the actual time. And you can see that blue is the amount of time how long it ran, and then the gray is each task under those titles of final presentation, midterm presentation, and proposal draft, breaking it down to showing how many days were spent doing these specific tasks that were able to meet these requirements. So for some deliverables and future work, so in Senior Project 1, we were able to find and clean a data set. We were able to create 3 machine learning models, SVM, MLP, and ID3. We were then able to evaluate the results and then compare this to previous research shown in the comparison table. Some things to focus on in Senior Project 2 is we're going to shift to more malware imaging data sets and using deep learning models, because this is more relevant to today's research in cybersecurity, and being able to work on these machine learning models on the CICIDS dataset really built a great foundation for me being able to achieve this in the second part of Senior Project. So traditional network intrusion detection systems rely on patterns and static signatures to detect attacks, which can miss new attacks. Machine learning models can learn from data to detect unknown and known attacks. The dataset we use, CICIDS 2017, provides a realistic environment for testing machine learning models, gives the 7 days, benign and attack traffic, and then we were able to evaluate results from machine learning models to improve accuracy while being able to maintain as low of false positive and false negative events. Here are my references. Thank you for listening to my presentation. If you have any questions, please let me know. Thank you.